Okay, good evening. This is our 30th lecture. In the previous lecture, we have started our discussion on the measurement of the velocity, and in terms of velocity measurement, if you see, our interest is to measure the local velocity at each and every point. Okay, with that, we have started discussing about different measurement techniques which can be used for localized velocity measurement, such as laser Doppler velocimetry, hot wire anemometry, and the third one was particle image velocimetry. Specifically, we found that laser Doppler velocimetry has not much applications for multi-phase flow applications, and then we have seen that hot wire anemometry, how it can be deployed for measurement of the velocity field in multi-phase flow problems. Today we will again continue our discussion on the similar topic, and we will try to see a slightly different technique, which is a particle based method and called as particle image velocimetry. And subsequently, if time permits, then we will also look into uncertainty analysis, which almost every time we have to perform when we do the experimental measurements. Let's talk about particle image velocimetry. So as the name suggests, what we are doing, we are basically using some seed particles. We are seeding some particles in the flow, and then we are trying to capture the images of these seeded particles, and based on their consecutive images at some specified time interval, we try to locate their positions, and that we correlate to measure the local instantaneous velocity. So the one of the benefit in comparison to hot wire anemometry in case of particle image velocimetry is that it can give you simultaneously the velocity profile at all the locations which you have actually photographed. Okay, so typically if you see the setup of a particle image velocimetry, so this is a pipe, so say this is the cross section of a pipe, and this is the pipe in which say flow is taking place. So when the fluid is flowing in this pipe, along with fluid, from the entry point itself we have seeded small particles. So small particles means their size is somewhere of the order of micrometers, and typically these particles are called as typically the particles used for this type of measurements are neutrally buoyant particle. Okay, so I think now all of you know this term neutrally buoyant, because earlier also while we were doing the flow over particle analysis, then also we have used the term neutrally buoyant. So the meaning of neutrally buoyant is that particles response time is so small in comparison to the flow time scale that particle will exactly try to follow the flow field. Is this point clear? What is the meaning of neutrally buoyant particle? So we know that whenever a particle is placed in a flow field, it is having some response time. Okay, so particle is having some response time, but particle is so selected that its response time is negligible in comparison to the time scale of the flow fluctuation. So because of this, whenever flow will be changing, particle will be immediately adapting to the flow situations. Okay, so it will not show any separate hydrodynamics other than the flow dynamics. So the question is, the important point is, all these particles which we are using, these are nothing but neutrally buoyant particles. Okay, so once I have seeded these neutrally buoyant these neutrally buoyant particles will be now present in the entire volume of the pipe. Okay, so after this, what we need to do, we need to eliminate these particles so that only we are getting the particles which are lying at a particular plane along the length of the pipe. Okay, so to do that, we will be using some, say, laser source. So this is a laser source which is sending the monochromatic light, and then we are using some optical arrangement in order to convert this beam of light into a thin sheet of light. Is this point clear? So now what will be happening? The particles which are just lying on that sheet of light, only these particles will be eliminated and other particles will not be captured by camera. Okay, so their intensity will be more. So because of that, whenever you will be capturing the camera, so typically camera is placed perpendicular to this plane, and when you are recording the photos, you will be only getting the particles which are just coinciding with the plane of the laser sheet, and all the particles which are away from the plane of the laser sheet, these particles your camera is not recording. Okay, so this is the basic setup, and typically this first type of arrangement is used when we are doing the single phase flow measurements, because in case of single phase flow we are not having any interface present. Okay, on contrary, when we use the multi-phase flow, then the whole setup is same, the only difference is we use two cameras. Okay, one camera is to capture the particles and other camera is to capture the location of the interface, because we have to also differentiate in between the phases. So to differentiate between the phases, we will be using one camera with some filter which will not capture the particle locations. Okay, and other camera will be used to capture the particle locations. Okay, so in case of two phase, if we have to employ the same setup for measurements in two phase flow, then we have to use two cameras. Now, the basic setup includes tracer particles, and these tracer particles will be considered ideal only when they exactly follow the motion of the fluid. And the particles which exactly follow the motion of the fluid, these are called as neutrally buoyant particles. So that is first condition. Second condition is do not alter the flow or the fluid properties. So whatever particles you are seeding into the fluid, okay, so their size should be so small that it is not causing any wake structure or other type of things which is actually influencing the flow field. And at the same point of time, whenever you add particles, it may happen that your final mixture, which is the main fluid and the particles, its properties should also not change. So particles should be seeded in such a concentration so that the properties of the overall mixture are not actually influenced. Okay, and third important point is the particles do not interact with each other, because many times what can happen, what can happen that say if two particles are joining together, then you will not be able to trace the particles new location. So that's why while you are seeding the particle, the concentration of particles will be such that so that no particles are actually interfering with each other. Okay, so there should not be any loss of particles by coalescence or say splitting of a particle into multiple particles, because that will be giving you the errors in your measurements. Okay, so these three conditions should be of tracer particles. Yes, from the laser source always there will be a only point light. Then you have to use a cylindrical lens which will be actually diverging it, and then again you will be using a spherical lens which will be converging it in the form of a parallel sheet. Okay, so some optics you have to use in order to convert this light into a sheet. Okay, so that optic setup one has to use. In this zone, so whatever your illuminated portion is there it will be entirely capturing the particle images. Okay, then what generally we do, we give two or more short laser light pulses with a known time separation, and then these illuminate the tracer particles, and thus particles appear with spacing proportional to local velocity. So the meaning is, say once you have given a single laser pulse, so corresponding to single laser pulse, say you have got some photograph where particles are something like this. Then you have given another pulse after some time gap. Okay, so once you have given the second laser pulse after some time gap, then what will be happening? All these particles will be occupying now the new locations, and of course their new locations will be what? Yes, so because of the local velocity of the flow during that time interval, how much distance a particle can travel, corresponding to that they will be having the new locations. Okay, so if you can trace these new locations and then you can just differentiate the distance and time interval already you are knowing, then you can actually calculate the values of velocities. Okay, but now you will be finding that, say, if you have, say, so many number of particles, how to identify that whether that particle has gone to which? For example, this particle can go to any of these locations. So that is something which we have to see how the people how this is done. Okay.
सर इस केस में तो सिर्फ वही पार्टिकल्स कैप्चर कर पाएंगे जो प्लेन के बिल्कुल पैरेलल वेलोसिटी हो जाए.
Yes. No, not parallel to plane. We can capture velocity in any direction, but
पैरेलल.
yes, velocity is parallel to the plane.
सर क्योंकि वो कोई भी परपेंडिकुलर
Yes.
कंपोनेंट हो तो लेजर के बाहर आ जाएगा.
That particle will be leaving out of the frame. Okay, so only say if you have this seat, so in this seat one component you can measure this and other component you can measure this.
सर वो भी तो हम कैलकुलेट कर ही सकते हैं.
The third
डायमीटर अगर पार्टिकल मेरा पास आ रहा है, पर्सपेक्टिव डायमीटर बढ़ जाएगा उसका.
that you cannot do, because that is something, the particle itself is so small and that you cannot even identify particle, that which particle has gone to what place. So identifying their perspective diameter is very challenging.
वो लेजर शीट की फ्रेम से ही बाहर आ जाएगा.
Yes, the frame of the laser sheet is of the order of some micrometers and it may come out of that. Okay, so that's why with this you will be getting a two-dimensional planar velocity. Okay, and now if you have to see the third component of the velocity, then you have to eliminate in other direction. So you have to make your laser sheet in this plane. Okay, and there are techniques which are particularly called as time resolved PIV or high speed PIV measurement systems. What these time resolved PIV can do, this can actually, you can keep on swapping the planes in depth direction and you can measure the velocity at multiple planes in very small fraction of time. So that all depends upon the your system capabilities. Okay, is that point clear? Okay, so of course then we have to use some electronic cameras for recording the particle images. Now when we have captured the images, then we have different methods. Either we can use autocorrelation, or we can use cross correlation, or we can use particle tracking velocimetry. So these are nothing but the background algorithms which one has to employ in order to identify the images. So how this is done, let me give you some crude idea. So say you have a frame, okay, and in this frame you have some particles. You will be having actually so many particles. So this is at frame, say at some first pulse of the laser which is given at time interval t1. Then say between two laser pulses you have the time gap of delta t. So you will be having t2 time which is t1 plus delta t. Okay. Now you will be having some new particle locations. But it is hard to predict that this particle has gone to which location. So what typically is done, first in the first frame, this entire frame will be divided into a large number of subregions. Okay, so you will be having this frame now is divided into large number of subregions, and this subregion space is chosen in such a way so that each sub-region contains at least of the order of around 10 particles. Is this point clear? So good number of particles each sub-region should have. Now this new frame is also divided into same number of sub-regions. So new frame is also divided into same number of sub-regions. Now what you will be doing, each sub-region, okay, each sub-region from this first set will be cross correlated with all the sub-regions of the new image, and the point where you have highest value of the cross correlation function, that point you will be saying this grid has highest probability of reaching that particular place. Is this point clear? All are clear with this idea? So we are not tracking a single particle, but what we are tracking? We are tracking a single grid. So what will be happening? Let me zoom in into this single grid. So if I zoom in into this single grid will be looking something like this, and it has say some particles somewhere. So of course these particles, corresponding to these particles, your signal value will have 1, and at all other locations you will be having signal value equal to 0. Now when you are cross correlating this with first one, so if your this signal of intensity is cross correlated with this one, and it is giving you say cross correlation function, this is say 1, this is 2. So if you are getting R12 value is 0, it means this frame is not at this location. These are not correlated. Then say this frame you have correlated with this grid. When you have correlated with this grid, then say you have got the value of R12 as something like this. When you have further correlated with this grid, then you have got even more larger peak. Whenever you will be correlating with all the subgrids in the new image, and for each one where you will be getting the largest value of the peak, there you will be saying that is your actually location of that particular grid. Okay.
So multiple large peaks are there.
One peak you will be getting which will be highest value. So the highest value peak you will be
अगर
choosing.
दो highest value peak बराबर है
सर हम ये कंप्यूट करेंगे कि जो पार्टिकल्स उस फ्रेम में थे वो इस वाले फ्रेम में थे।
Yes.
इसमें तो एरर का ही चांस नहीं होता।
Of course, there will be chance of error also. So that's why you have to do many times iterations also. You have to change pulses. You have to select the value of delta t. Okay, different values of delta t. You have to decide that for what velocity, what should be your value of delta t. So all these things actually you have to do. So this is not like measurements are not very easy. That okay, you go switch on the button and then you have got the output. You have to do some trials, and then you have to identify that which velocity is actually your physical one. Okay. So like this, when you will be cross correlating, say the cross correlation with this image is highest. Now you know the grid locations of this frame. You know the grid locations of this one. So you can see what are the displacements delta x and delta y of this grid with reference to this origin point. Once you know the displacements, then delta x by t and delta y by t will be giving you the velocity. And what is that velocity? That velocity is applicable at corners of this grid or at the center of grid. So whatever, whether you vertex centered or say this cell centered approach. Okay. So depending upon that, you are not getting velocity because of the location of the individual particle motion. You are getting velocity because of these grids. So what will be your spatial resolution? Your spatial resolution will be depending upon the resolution of the grid. Okay. So resolution of the grid. Have you understood what is the meaning of spatial resolution? Means, say if this is your visualization window in this visualization window, one velocity will be known for this point, other velocity will be known for this point. Okay, so if I take this type of arrangement, then I will be having one resolution. If I take these subframes, then what will be happening? My resolution will be better, but computations will be more so expensive. Okay, so because your number of grids in which you have to do the cross correlation, that has actually increased. So once the number of grids are increasing, though your spatial resolution is actually improving, but ultimately your computational power will be increasing. Okay, so it means that whenever you do the PIV measurements, it is not only that say you have captured the images. Once you have captured the images, you are having images in raw form, then you have to select different values of delta x, delta y and delta t, and then you have to see for what values you are kind of getting convergence. Because if you choose very large delta x, delta y, then what you are saying that will happen, that multiple regions may have chances of getting match. Okay, so that's why what we need to do, we need to further refine the size of the subframe. So once we are further refining the size of the subframe, then what will be happening, then again the chances of getting cross correlations with multiple images will decrease. Is this one clear? But the issue is that if we go for whatever is our size of the grid, actually that is the spatial resolution. Okay, so we cannot go less than the size of the grid.
जैसे ऊपर से हमने स्टार्ट किया, ऊपर एक रो ले ली, उसका क्रॉस कोरिलेशन
For each and every subframe.
सेकंड रो पे आ गया तो वो पिछली वाले से उसका कोरिलेशन निकालेंगे.
Yes, for each and every.
तो वो तो मतलब पहला कॉर्नर वाला मान लिया हमने, और सेकंड रो में सेकंड जो एलिमेंट है.
See this one, this one, this one. So likewise, 1, 2, 3, 4, 5, 6. This is having say numbering A, B, C, D, E. So 1 has to be tested with all A, B, C, D, E. Then 2 has to be tested with all A, B, C, D, E. Okay.
सर अगर लेफ्ट वाले ग्रिड में दो आपस में कोरिलेटेड है ज़्यादा, तो वो सामने वाले फ्रेम में भी तो कोरिलेटेड सिर्फ एक ही पैच के लिए होंगे.
No, so that is what we will not be able to see the correlation over here. Okay, because what we are doing is we are at the inlet, we are dispersing the particles, then depending upon the local velocities they are identifying some locations. Okay, so the point is once they have once they are in individual local velocity positions, so corresponding to that they will be actually going.
मेरा क्वेश्चन ये है सर कि एक पैच के लिए
For this patch you said that auto correlation in this frame. Okay, so in this frame you will not be comparing two. First point is that because this frame is at same time instant, so already you know that if this frame is at same time instant, then already you know that this frame is particles at this frame cannot be correlated. Okay, because these are nothing but all the particles at the same location. Now the important point is when you are taking this frame at t2 time, at t2 time it cannot happen that all the particles of this are moving through same distance and all the particles of this are moving through same distance, because their individual local velocities will be different. May not be for all particles, but for some of the particles these will be different. So that's why chances of getting that type of match are rare.
सर सारे फ्रेम्स के जो ग्रिड साइज होंगे वो इक्वल होंगे.
Yes, mostly grids are taken structured grid, because from computation point of view that is actually the more appropriate arrangement.
सर सेम ब्लॉक के लिए मतलब माने आपसे एक फर्स्ट जो है वो डी के लिए कोरिलेटेड है और थर्ड भी क्या डी के लिए कोरिलेटेड हो सकता है, ऐसा
No,
हो सकता
no,
है?
no, no. That type of chances will not be there. Because if one set is clustering there, then of course the second has to move in some other location. So means all the grid sizes should form there also the entire frame but slightly shifted. Is this one clear? Because then only you will be having the
Velocity.
correct estimate of the entire velocity. So means say this has shifted slightly, so other will also shift slightly. So ultimately, two grids will not be intersecting over each other. So if two grids are not intersecting over each other, so of course their frames will be having the same distance. Okay. I think you have developed that code na in DP for PIV.
No, sir.
Acha, that was in MTP project, right? One of your senior, I think he graduated, he has developed one PIV prototype in MTP with, I think, Dr. Gajendra Singh.
Yes.
So, okay. I forgot his name. He has demonstrated once in
I also forgot his name. But I
MTP.
know the face.
I also know the face. Okay, so that is so this type of correlation which I have told you, that was actually cross correlation when image 1 and image 2 were taken at certain time pulse and then these two are correlated. In case of autocorrelation, what is done, image 1 and image 2 are actually superimposed on a single frame, and then if you are just taking a single frame and there if you are trying to correlate, then we say autocorrelation. Okay, so it means particles old locations and new locations both are captured on a single frame. So that is when we are using that type of system, then we call as autocorrelation. Now third method is particle tracking velocimetry. So particle tracking velocimetry is something which is not yet commercially being used, but this is the ultimate thing which can actually give you better spatial resolution. Okay, so the meaning of particle tracking velocimetry, as the name suggests, now we are not interested in tracking the grid, now we are interested in tracking the individual particle location. Okay, so with the now we have so many developments in computational mathematical computing, such as fuzzy logics, AI, machine learning. So by using all these methods, if you go to little bit more advanced data analysis techniques, then if someone can even capture the particle locations, then you can even get the better resolution. Okay, is this one clear? So in comparison to grid-like arrangement, what we have seen, the particle tracking velocimetry will be having always the better resolution. Is this one clear? Okay, that already I have explained. Yes, so third point is image is divided. This is also I have told you into small subregions and each contain around 9 to 10, at least 9 to 10 particles, and then spatial autocorrelation function of the region with itself is calculated. So this is the autocorrelation function, already I have explained to you in the previous class. So say f of xy and then f of x plus delta x and y plus delta y. So when you will be, what you are doing basically, say you are having one subregion here, and if you consider that in the new frame you are creating subregion like this, which is displaced delta x in x direction and delta y in y direction, and then you are trying to find out the cross correlation function. Now for whatever values of delta x and delta y, you will be getting the highest value of the cross correlation function. You will be considering these delta x and delta y are your actual actual displacements of that particular subregion. Is this one clear? Then we have, by iterating this procedure, of course, over all the subregions, the whole velocity field is retrieved. And in recent systems, two images are captured on separate frames and a cross correlation between corresponding subregions is actually done. So in old systems, this was done when camera used to capture both the particle images on a single frame, but nowadays actually both the images are captured separately. Of course, based on autocorrelation and cross correlation, we will be having limited spatial resolution because this is limited by the size of the small subregion. Okay. And then particle tracking velocimetry, where determination of displacement of individual tracers we can do, so that will be giving the highest spatial resolution. Okay. So new algorithms such as pattern recognition and neural networks, genetic algorithms, fuzzy logics, etc. can be employed in order to go for the particle tracking velocimetry. Okay. PIV techniques can be easily used for multi-phase investigations, but provided one condition that we should be able to differentiate the two phases. Okay, so if say two phases are looking like similar on a camera, then actually these cannot be employed on multi-phase flow measurements because particles will be giving you the velocities, but along with the velocities you have to also identify where is interface. Okay, then only you can do the actual multi-phase flow measurements of velocity. So for capturing interface we need another camera, as I told you previously that for multi-phase flow problems we use two cameras. So one will be capturing the interface and other will be capturing the particles. Okay. So use of fluorescent tracers with double camera image acquisition setup is one way to solve this problem. And when we use optical filters, then we can separate the radiation scattered by fluorescent and the neutral particles. Now, when we use the particle image velocimetry for multi-phase flow problems, typically when interfaces are present, there will be some errors in measurements near the interface, and these errors are called as actually spurious currents or spurious velocity vectors in the PIV measurements. Okay, so how these spurious velocity measurements can come? So typically say this is a gas bubble and this is a laser sheet. So when your camera will be sending some ray, that ray can have multiple paths. One path is direct path which will be capturing the real particle position. Second can be this ray can have this particular path when it is reflected from this point and then going at this point, and likewise if it is returning it will be giving particle location something like this, which is called as a reflected particle. And second can be it can actually refract at two places and then it can give third particle. So it means for a single particle you can get three images. Okay, so two hypothetical images of reflection and refraction from the interface. So near the interface when you have reflections and refractions, because of that actually you will be getting errors in your measurements. So you will get some virtual particles. So now let me give you some idea about what should be the characteristics of the light source which we are using. So first requirement for light source is that it should have a short duration of illumination. Okay, so it should just illuminate for very small duration. Then your camera will be capturing for that duration, then again a small time interval and then the next pulse. Okay, so typically when we do PIV, when we have this PIV setups, there are two different types of setups. One is called as low frequency PIV measurement and second is called as time resolved PIV measurement. So low frequency PIV setup is typically used when we are having the steady velocity measurements. Okay, so we are not much interested in huge number of pulses. Okay, but when we are going for the turbulent flow situation, so in case of turbulent flow situations, what will be happening? At each and every time instant, we will be having different values of the local velocities because of the turbulent fluctuations present in the flow. Okay, so under these scenarios, what we do, we have to have very high speed of laser pulse generation and high speed of camera to capture the images. Okay, because then only we will be able to capture the local fluctuations present in the flow. So that type of PIV setup is called as time resolved PIV. And of course, because the requirement is of high frequency measurements, so the cost of the time resolved PIV will be more in comparison to cost of a लो फ्रीक्वेंसी PIV मेजरमेंट.
सर हम लाइट को पल्सेस में नहीं करते हैं, मतलब अगर लाइट सोर्स कांस्टेंट भी है तो हम सिर्फ कैमरा की फ्रेम्स में ही टाइम डिले डाल दें तो भी चल जाना चाहिए.
Okay, so you are saying that say you have a constant light source which is making a fixed seat, but just you are making this camera as the
We are capturing at different time steps.
different time steps. So ultimately what will be happening, if you keep a fixed type of light seat, so you may feel that say fluorescence and scattering may not be very frequent or sharp intensity which is captured by the particles. But once you will be just creating a pulse, then you will be getting sharp images because of the simultaneous scattering of light from camera ray as well as from the laser seat. Okay, and typically when we say the this one light pulse, why it is needed, many times whenever we do the PIV measurements, we are not interested on PIV measurement in a single plane. We are interested in PIV measurement in say subsequent number of planes along the depth of the pipe. Okay, so when you have to do that, then what you will be doing, once your laser light source will be illuminating first plane, after some time it will be illuminating the second plane, after some time it will be illuminating the third plane. So then also that particular type of setup is called as actually stereoscopic PIV, with the help of which you can make even three-dimensional velocity fields, and their cameras are placed at two certain angles. So their requirement is to continuously change the location of the seat. Okay, so once you have that much, once you have the requirement of that type of pulse, then you have to go for this type of lasers. Okay. Second is practical criteria for choice of maximum duration of each illumination pulse is that particle images do not appear as streak but appear as regular dots. Okay, so I think here your first question is also now partially answered. So if you keep your light continuously on and then if you capture with high speed camera, so what will be happening, the frame rate of capturing camera will be fast, and if your illumination is continuous, in your image, instead of getting the individual particle locations, your frames will be like streaks. It will try to capture the entire particle path. Okay, because say what you are doing, you are continuously illuminating and your camera is capturing at the high speed. So whenever it is capturing at the high speed, if you don't have simultaneous match in between the illumination of the particle and the camera ray, then what will be happening, that particle movement will appear as continuous streak, and in your frame you will not be getting the individual dots but you will be getting a line. Okay, so that's why your light source should also have pulses, because if you have continuous one, then it will be appearing as a line rather than a dot. But for your accurate measurement, it should appear as a single dot. Third point is, when the particles are displaced within the pulse duration, so it should be significantly smaller than the size of the particle itself. Okay, so it means the delta t of the pulse should be so small that particle has displaced with displacement lesser than the size of the particle. Okay, so that is third requirement. So typically this is delta t should be less than d tau. So d tau is displacement, d tau is size of the particle, and v is velocity, and m is magnification factor. So velocity into delta t represents basically the distance traveled by the particle. So distance traveled by the particle should be smaller in comparison to the size of the particle between two pulses. Is this one clear? Then illuminated particles are distributed within a thin sheet such that they can be imaged in focus, and their position in depth is dictated by the light sheet. Okay, so of course the sheet should be thin, then only we will be able to get the planar particles. Otherwise what will happen, some particles may come in one plane, some particles may come in other plane. So that will of course give the errors in the measurement, because ultimately what output we are getting as a single two-dimensional frame. So if we are getting a two-dimensional frame, all the particles should also be of that particular two-dimensional frame. So if particle is coming from a thickness, then few particles are in one plane, other particles may be in other plane. So what I am trying to say if your sheet is thick, say this is the thickness. So if this is the thickness of the laser sheet, then all the particles which are lying at different locations, these are captured. But in the camera, it will be seen as a single two-dimensional frame. Okay. So then, where to locate that position? So if the laser sheet is very thin, so whatever small thickness you can achieve, that will be the most accurate for the measurement. Is this point clear? Otherwise, you will be able to see the particles in depth in a single two-dimensional frame. Okay. Then intensity of light source must allow scattered light from the shading particles to be detected by the digital imaging device. So of course the intensity of light you should select in such a way so that camera is able to detect the scattered light. If camera is not able to detect, then once again you will be having wrong measurements. So typically the energy of the laser pulse is proportional to linear dimension L of the area of interest. So whatever is your visualization window size, depending upon its length, your energy increases if length increases. And typically 100 millijoule energy is sufficient to illuminate an area with length equal to 10 centimeter in airflow, while about twice the area in water flow, where in case of water actually illumination is better. So that's why low energy can give you the better illumination in comparison to air particles. Okay. Then lasers which are used as illumination source, they can produce a pulsed, collimated and monochromatic light beam. So why this is needed? Because if light is not collimated or monochromatic, in that case it may happen that some particles may appear brighter, some particles may appear with some low intensity. So almost all the particles should appear of same intensity. So that's why your light should be monochromatic. Okay. So these are commonly used tracer particles. So you can see if you have air present, then even liquid droplets can also used as this glycerin water solution. So this is a common solution which is available. So the droplets of glycerin water within the diameter of 1 to 3 micrometer can be used as tracer particles. And if you have water, then typically we will be having actually some solid particles as the tracer particles, okay, and their corresponding sizes and densities are also given. So typically the size and densities should be so small that they are neutrally buoyant, because if they show their individual hydrodynamics, then your measurements will be wrong, okay. Then this is the typical measurement strategy. So in first case you can see the low image density is there, and in second case you have high image density, and here you can see that this particle is having, so say if these open circle particles are the previous location and filled particles are the new location, so then each particle is having so much possibilities to move, okay. Now depending upon these possibilities, the possibility with which you will be getting highest peak, that will be considered as the new particle location if you are using particle tracking velocimetry, okay. And this is the typical image of velocity vectors which you can observe from PIV. So here you can see all these are nothing but velocity vectors, and all these velocity vectors are obtained from the PIV measurement, okay. Now in these velocity vectors you can see majority of the vectors are represented with black color, but few are represented with this dark yellow color. So here you can see this. What are these? If you see, these appear completely different than their surroundings. So surrounding flow field is oriented in one particular direction, and these are having slightly higher magnitude in comparison to their surrounding local velocity field, and even their directions are also arbitrary in comparison to the surrounding local velocity field. So these are typically called as spurious velocity vectors, okay. So here you can see one good estimate that if you plot all the displacements delta x and delta y, okay, all the displacements delta x and delta y between the two frames for all subframes, you will be finding that majority of the displacements will be clustering in some single domain, okay, because your time interval is so small. So whatever your small grids are actually moving, these will be depending upon the neighboring velocity fields. So that's why your displacement should also cluster near the single zone, but some displacements will be completely out of this clustered domain. So these are nothing but all the outliers which are resulting in spurious velocity measurements, okay. So whenever you are doing PIV measurement, once you have done analysis, your task is not over just by plotting the velocity vectors. You have to also find that what are the spurious vectors or outliers. And typically whenever you do multi-phase flow measurements, these spurious vectors are more prone to appear near the interfaces, because near the interfaces you may have presence of virtual particles because of reflections and refractions, okay. So that's why near the interfaces the chances of getting spurious currents are spurious velocity vectors are actually
तो
more.
सर इनको रेक्टिफाई कैसे करते हैं?
By using some filters in
मतलब डेटा हटाना है,
yes,
फिर सर वहाँ पे अगर हमें वेलोसिटी वैल्यू चाहिए,
not all data we will be removing. We will be identifying what are the bad data points and we will be removing only these, okay, not all. Now once you have done measurement of the velocity, then you can use this velocity even to plot your other quantities such as rotation, deformation or vorticity, etc. Okay, so say if you have to calculate vorticity, so if this is xy plane, this is x, this is y. So if you have to calculate vorticity, what is vorticity? Del v by minus, okay. Say you have to identify vorticity at this point. This is the location where you want to calculate vorticity, and you know the values of u and v at all these points, Okay, because once you have all the subgrids, then you know the values of velocities in the entire domain. So now you can simply use your finite difference approach. So as per finite difference approach, del v by del x will become,
V2 minus
in terms of x, I have to move. So j will be fixed. So v at point I plus 1 comma j minus divided by, say this gap is delta x. So it will be 2 delta x. If this is, what is the order of accuracy? Okay. And then similarly del u by del y, you can calculate u at I comma j plus 1 minus u at,
I comma j.
sorry, this is, I am using 2 delta x, so I must use here
I minus 1.
and here order will be,
Square root. Second derivative.
this is not second derivative, na? So if I take second derivative, then I think square will come. In first derivative, it will be 2 delta x. In first derivative, it will be 2 delta x. Okay, go to your CFD notes of finite difference method. Okay, is this one clear? So it means that the how powerful is actually PIV tool. This you can see over here. So if from you are doing PIV measurement, then you can know the entire velocity vectors in your visualization window. But along with that, you can also calculate the other parameters such as vorticity, deformation, rotation, etc. Okay, so this is the utility of particle image velocimetry over here, and in comparison to other methods of velocity measurement, this is more, you can say, no, efficient. So what you are doing there, if you use hot wire anemometry, first you have to put the probe at one location, then you have to put probe at second location, third location, so at multiple locations. That will be becoming a time consuming process. Okay, here what you are doing, in a single go, your entire visualization window you are actually able to capture. Okay, so this is 2-dimensional measurement. Same PIV setup can be extended for 3-dimensional measurement. When we use this for 3-dimensional measurement, then despite keeping camera normal to the frame, we keep cameras at certain angle, and then whatever the two images we are capturing, we will be applying certain transformations in order to convert these two images into a 3-dimensional space. So that is called as stereoscopic PIV. So that will be involving nothing but more transformations in terms of mathematical computations. Okay, and then we can actually capture the velocity field even in a 3-dimensional space. So let me stop now, and we will discuss about the uncertainty analysis and other things in the next lecture.
Square root.